Hello everyone, it's December 15th, and as usual, we're going to do December 16th right now. Alright, it's been, I think, the past 2 days, maybe 3 days, we've been not doing very well. I kind of blame the time, as usually when I do the LeetCode at night, which is right now, after a full day of work, um, the brain gets mushy. But I still want to do it at night. I mean, for one of the reasons is I want to get back to the contest, and for me, the contest starts at 9:30 p.m. So I better get used to thinking at night. But still, yesterday was pretty bad on the second question. We failed to realize how the problem can be converted into merging case sorted list. So that was a bummer. All right, but we're gonna go do today. That's what we have. So first one is minimum height trees. We've done this back. Yeah, so if you remember, that was yesterday, right? Yesterday was 11:02, and today is 11:04. A tree is a undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes labeled from 0 to n minus 1, in an array of minus 1 nodes, where edges indicates that there is an undirected edge between two nodes, ai and bi, in the tree. Okay, so ai and bi. So I need to turn this into adjacency list. You can choose any node of the tree as the root, which is true. And then you select a node x as, when you select node x as the root, the result tree has height h. Among all possible rooted trees, those with minimum height are called the minimum height trees. Ah, I remember this one. I don't know the solution, but I remember this one. I think you can do some type of pruning, but I forgot how to do it. Return a list of all minimum height trees, root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and the leaf. So example 1, with edges 1, 0, 1, 2, and a 1, 3, output is, this is the 1. The height of the tree is 1 when the root is the node with label 1, which is the only, yeah. I mean, these are all identical. So 3 and 4. Okay. ai is not equal to bi. All pairs are distinct. A given input is guaranteed to be a tree. There will be no repeated edges. All right. What do I remember? Don't remember at all, honestly. I mean, I think we can go, we'll take anything as the root, right? And then its height will equal to the maximum height of its children. Right? So like if I want to find the height of 4, we are looking at the height of 5 and the height of 3. And height of 5, right? Height of 5 is, because 4 is, so again, height of 5 is 0. So on this side is 0. And on height 3, we have the height is 1, right? And then therefore, if we find height 4, the answer is 2. The height is 2. Now, if we want to try to find height 3, right? So on height 3, I computed as 3, we have this node and this node, right? So one height 3, so I'm going to find the height of this, this, and this. So height of these. So if I can get the height of each node, so each node has neighbors, right? So if I can find the height of a node, that's like if I have a node is here, and then I say if this one of the node is treated as my parent, then what is my height? And in this case, I need to find a height. So these height now I need to find a height of 4, right? Let's say I already find a height here. The height here says we have 5 and 3, right? So if this is a root, and I say on a 5, so I'm going to find a height of 4. And the height of 4 is 2, but that's 2 is because on a 3 I have 2. So on 5 I only have 1. How did I resolve it last time? Aren't we looking for the? Aren't we pruning? I think, yeah, it is pruning, right? We look for the edges. What is edges? The leaf. The leaf is the node that only has 1, because the minimum height tree will be very flat. I want it to be very flat. So I can look for the node that are leaf. Like this is considered leaf node because it has only 1 connection, right? I shouldn't say just the number of connections. The number of connections. So these nodes have 1 connection. So I can prune them, right? Cut them, and then from them I can go to the next level, right? So the next nodes will have at least 2 connections. But after this is severed, so when I check how many connections they have, so we're gonna just prune. Yeah, I think it's a pruning method, right? So we go through all the nodes, we find the node that only have 1 edge, right? And we push all of them into a queue. And then we pop them out. Everybody pop out. We are going to remove this edge, right? And when we remove this edge, we're gonna look for the node that connects to the edge, right? And I'll remove it and then count how many edges this next node has. And if this next node only has 1 edge left, and we push that into the queue as well. Okay, so we're just pruning the nodes have only 1 edge, right? And then the remaining has 1 edge, and then we prune it again, right? Until when? Well, until, so in this case, if we prune, this one will push 4 into it, right? And this one push 3 into it. And this one, 3 is already in, so we don't have to push. So prune, prune. So now, what I'm pointing out is 3 and 4, all right? So now 4 point out, I'm going to prune it. And if I prune it, then 3 will have 0 edge. 3 will have 0 edge. So what are you saying? Well, I think what I'm saying is it always end up either one node, right? Or 2 nodes. Could it be 3 nodes? What if, like, at the end it's 3 nodes? What's gonna happen? Right? If we prune, and now 3 nodes, then we have, if 3 nodes will definitely go to 1 node. So it's either 1 node or 2 nodes. Yeah, it's either 1 node or 2 node. Because if we prune the edge with 1 node, right, and however complex, we can prune, and eventually we either end up with, if we end up with 3 nodes, and it's a tree. So if we have 3 nodes, there's no one way to have a tree with 3 nodes. It's just a line, right? That's the only way to have a tree with 3 nodes. There's no other way. And if that happens, then we can keep pruning, and then we'll get 1 left. Now, if we prune have 2 nodes left, then those 2 nodes, there's no more way to prune, right? No more way to prune. So in that case, we can use this pruning method. I did remember that a year ago when I was solving this problem, I was using a different method, a more convoluted method, which surprisingly I'm not able to think about. I'm not able to figure it out right now. It's feel sluggish. I feel tired and sluggish. Tired and sluggish. The head is spinning. All right. Okay, so how do we pruning? How do we do it? Well, we do it by first to turn this edges thing into adjacency list, right? Yes, we're going to turn that into adjacency list. So adjacency list is going to be, not like it to be just a dictionary, but okay, it's default dict. Default dict. So this one is going to be a default dict list, right? And then for AB in edges, what is the aim used for? Oh, we don't want you to use default dict. Yeah, okay. I don't need to use default dict. I can use this for this in range n. Right? I can use this. So I say AB then we say adjacency A dot append B adjacency B dot append A. Right? So we get adjacency list. Now what? Now we need to create a queue, right? Create a queue. Queue shall be the edges that has only one edge. We know that only has one edge. So there can be for I in range n, right? I will say len I if len adjacency I is equal to 1. Alright, so we pick those out and say while q temp is this for for node in queue, right? For node in queue, while len this is larger than 2. So for node in queue, we need to remove this node, right? So how do we remove this node? Because I know this one only pointed, so I know the next node, right? We can get the next node. And after we get the next node, we can remove it from the other one. Okay? Therefore, shouldn't this be a set? That'll be easier. We can just do add. Okay? So for node in queue, and we say, what do we say? For node in queue, and this can actually be a set as well. I can make this into a set as well. Everything is a set. So for node in queue, next a neighbor, right? The node has only one neighbor, so neighbor will equal to JSON list node 0. Turn this into a list. Grab it. That's the neighbor. Then JSON neighbor dot remove node. If len JSON neighbor, if len this is equal to 1, then temp dot add neighbor. Right, and then we go blah 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 blah. When we finish, we can say q equals temp. Back up, so when we're done, q pop out, and then return list q. Okay? Alright, let's try this. So what test case do we have? First one, and it's 4. This answer shall be 1. Second one, I have a bunch of edges, and then 6. Three and 4. Next one, empty. Oh shoot! Do you check empty? 0. This one is 2, 0, 1. That should be 0 and 1. Yep. I don't know. Maybe it works for empty. Who knows? We'll see. Nah, it didn't work for empty. Alright, why does it not work for empty? If it's an empty set, what does that mean? It means we only have one node, right? We only have one node, and it's empty, and yeah, the edges is empty. Yeah, that's true. So we should return list q. Oh, we can just say here if. All right, we'll say if not edges. It happens if we only have one node. There's no edges. Then we always return 0. Okay. All right. Let's attempt this. See how it goes. Wrong answer. Damn. Okay. What happened? I have 3 and this. And draw it. I have 0 to 1 and 0 to 2. Answer shall be 0, right? And I got 1 and 2. That is strange. How? Oh, because violin. Hmm. The Q. The Q is currently inside. Okay. Nah, that's not good. So we keep going. In that case, well, let's say we only have 2 left, right? We have 2 left. If we have 2 left, then if a node coming out, a neighbor is the other one, and then adjacent neighbor will remove the node, okay? And then after remove, this is equal to 0, so I don't append. And I go the other one, right? The other one, and then neighbor remove, and then neighbor is also nothing, so I don't append. So I come back, Q is nothing, right? Q is nothing. Q is empty. So if Q is empty, then what do we do? Let me think. Let me think. We have the Q when we get to the end, right? The problem is when we get to the end, what do we do? Now, when we get to the end, all right, and if I remove, if the length is 1, if the length is 0, all right, that's that. If the length is 0, then that is our result. So I can have the result is this, and I can say while Q, blah, 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 say if this is 1, say elif, this is equal to 0. Then rest.append neighbor. And now I'm going to return res. That's not right. Hold on. So for node in this, right? We say if for node in Q, and I have a neighbor, and I can grab the neighbor, right? And then I'll grab the neighbor. I'll go to neighbor to remove my current node. Remove this node. Okay, so the neighbor doesn't have anything. But the current node still has the neighbor. All right, the neighbor doesn't have. And we say after the neighbor remove it, right? After the neighbor remove it, and we check. If neighbor is 0, we're not append neighbor. Okay, but how about the node? How about the node? Well. Yeah, how do we handle the last situation? The node, right? So if the node is by itself, then we definitely add it. If okay, I'm the node, all right? I am the node, and I say every time I get a node, it must have 1. Okay, if yeah, let's say the queue, it must have at least 1. Okay, so I get this node out, and I find its neighbor, right? I find its neighbor, and I find my neighbor. So for me, I need to delete my neighbor, and for neighbor, it needs to delete me, right? Okay, so neighbor is this, then do this, and adjacency node dot remove neighbor. All right, so when I remove both, I'm gonna check, right? Because me is gone. So if my neighbor has 1, I do this, right? If my neighbor doesn't have, then if my neighbor has 1, then we'll add my neighbor. And then when I see if, yeah, so remove, right? So I got the neighbor, and then I remove. And after I remove, then I'm gonna check. So node is done, right? I'm not gonna push node. So when I just check, say if len adjacency node is equal to 0, all right? Well, that's always gonna be equal to 0 because I don't have anything. Yeah, because I have 1, so I sever it, and then that's it. I'm gone. How do we handle the 2 scenario? How do we handle this? I only have 2 left. I can't just jump out with 2, because if I jump out with 2, then I run the risk of missing the 3 situation. Well, I mean, I keep prune, right? At the end, if it's a 3 situation, and then this one will prune and push this in, and this will also prune and push this in. Now it is by itself. Now when it comes out, it doesn't have anyone. then that is the solution. Okay. So if 2, if I can just push both in, right? And then when they come out, they check that they don't have any neighbors, then that's good. Okay, so now we have 2, they're connected, right? And then this one sever, and it has 1, and they have 1, so both push in. They both have 1, right? So come out neighbor. Neighbor equals, so this one's neighbor is this. And then I'm going to sever the connection. So we have, let's say, A have B and B has A. So now look in A, right? And then A has a neighbor B. Then what? And then I'm gonna say, because I'm gonna remove A, right? Now remove A. So from B's perspective, I'm gonna remove A. Ooh, from B's perspective, remove A. From whose perspective? Shouldn't from A's perspective I remove? If I say from A's perspective, I remove B. Then I'm gonna check. No, I'm checking the neighbor. B is the neighbor, right? So I say I'm gonna remove A. So A is gone. And then from B, I also remove A. Then B is by itself, right? And if B is by itself, I can push in as well. Then we only have B, we won't have A. How do we get to A? Well, what I think is, because we know the result is either 1 or 2, so what we need to do is set the queue. I'm going to check the queue's length, right? We can check the queue's length and say if q equals 2, then we check if these 2 are connected to each other. If they are, then we're done. If they're not, we keep pruning. How about that? Okay, then how are you proposing to do that? Well, I propose to do that by, we can come out if there's only 2. But what if it's like this situation? We have 2, right? And we're gonna sever, and then we get this. So we shall say while q is, well, if q is 1, then definitely. So while q is larger than 1, right? Temp is this. And then we're gonna say if, so node, okay, so everyone has at least 1, right? So for node in this, neighbor equals this, right? And we say if len q is equal to 2 and neighbor is in q, right? Then we're going to break. Now we're going to return list q immediately. That means we only have 2 left. Queued length is 2, and then it consists of the 2 nodes. Otherwise, Then we go to the neighbor, we're going to remove a current node, right? And so from the neighbor, I remove my current node. Okay, then I check my neighbor. So after remove me, I see how much my neighbor has. And the neighbor, neighbor has 1. Then I'm going to add neighbor, right? And then we'll go to the other one, and then I want to check again. So once it's done, I'm going to turn this to queue here. While len queue is larger than 1. Now these pass. So this is a special case of 2 nodes at the end. Man, I can feel it. I'm telling you, man, I can feel it. I can feel my struggle to concentrate and then just trying to figure things out. Yeah, it was not good. It's not good. No, we did pass, but man, I feel bad. Alright, so this one, I'm gonna just churn out all the solution I have in the past, and then kind of take a look. Oh, I have a official solution. 310. I remembered solving this problem using a quite convoluted method, but I'm not able to recreate that method again today. Thus, I have to resort to the smarter and easier method of pruning. So the rule of pruning is that we always prune the nodes that have only one edge. After each pruning, we add to the queue new nodes that have only one edge. This method can obtain the root of MIMT if the root is singular. If there are for the case where there are 2 MHT roots, I have to set up a separate, I have to set up a separate edge case, separate check for this case. All right, runtime. I think it's ON because each edge will be visited once, so I think that's ON. Now we run, I think it's like 200 and something. 220, 244, 51. Okay, let's read my solution. If it's too complicated, I just don't want to read it. The head is not in the right space right now. Yeah, never will. It's actually not that bad. Oh, it times. No, this one passes. Didn't time out. Get height. We have the adjacency list. We have the height. Yeah, we get everything, and then enumerate. If land children larger than 1, height equals self.get height root. So basically we say from everything we're gonna go get a height. So every node I go get a height. If height is smaller, then mean rest equals this, else height is equal to mean, rest out of pen. Wait, what is this? I just go through every single one and then find each one. I didn't cache, I didn't do anything, and it passes. Yeah, there's no cache. Basically, I take every one and I say if it has more than one, if it's children, if it has more than one children. What if I only have one children? What do I do? I just skip it. If it has one children, I just skip it. Why? Well, if a node only has one children, that means it's on the edge. I think that's probably my reasoning. If it has only one child, that means it must be on the edge, and I just skip it. What if I only have two? What if the adjacent list only had two? Ah, then I have a rest. Ah, I see. So if it's more than one, then I get a height. The height is from the current root, and now we want to find out the adjacency list or the child. If child is not, and I have a DP. Oh, I do have DP. If child not in scene and a child not in self.dp root. Self.dp root. So I think the DP is root child. This is root and the child. What is the height? Self.height from child. And then child height equals maximum child height. And self.dp root child. So the dp root child is at this root, right? If I take this as a root and this child, what is, so I do have to check the scene, and also I'm going to check if this has been set up in the dp root. If we're done, and now we return child HL. Yeah, so this one plus basically just traverse, right? We set up at each node, and then we go through all the children to find out the height. Okay. Slow, like when I'm trying to read this, it's slow. Oh, back then 220 is 98%. And today 244. Ah, this is the official solution, right? That's called topological sort. Layer by layer. Ah. Okay, so I have this. It leaves root. Uh-huh. Oh, remains. We use this. So remains minus equals leaf. New leaf. While leaf. Yeah, that's fine. It'll pop out. Dot remove. Hey, it's not a set. How can you do remove? So basically it's the same as this, but okay, we just need to change a little bit, right? Just need to change a little bit. So Q is fine, and we just need to remain is N, and then I'm gonna say while remain is a larger than 2. Really? Larger than 2? Yeah. Yeah, we do remain larger than 2. Because if it's 3, next one would be 1. Right? If it's 4, next one would be 2. Right. So remain is larger than 2. Temp is this. And in this case, we will need to use, I think I don't need a set. I can just use this. Temp is just this. So for no, so we're gonna say remain minus equal to len q, all right? And then for node in q, node neighbor, we don't need to check this, right? And then when we remove and blah blah, and let's try. Hand. Oh, then q is a list already. Here's remain. Update. Use remain to indicate when topological sort ends. Yeah, I think this one is faster. The only slow part is this. All right, but this one when you convert, it's only one value, so it's fine. But this is fast compared to this, right? Because this Jason's list is a list. All right, so we're pretty sure this is the right solution, so I don't have to check the actual solution. All right, let's see if this one's faster. No, it should be faster. Doesn't matter. These things happen. I don't know, like, why would it be slow? It's exactly the same. Neighbor. Yeah, it should be exactly the same. We'll do a line by line comparison. And the only difference is set and yeah, that's the only difference. I use a set, the other one uses a list. Did you see that? Initial condition. Yeah, adjacent lists are slightly different. These are the same. Leaves, they're the same. Yeah. Remain, 102. Remain minus, new leave is just temp. And for node, we'll get a leaf. And for child, in leaf. There's only one child. And then I can avoid converting to list. That's fine. So if a child, there's only one child. Because I only push in if I only have one child. And then I say the child, which is a neighbor, I'll remove, and if is equal to 1, and yeah, it's the same thing. It's the same thing. But I'm not going to sweat over this one. That's fine. Well, it's not early, so do we wanna? Yeah, I'll open the question. Let me take a look. Guess number higher or lower. We're playing a guessing game. The game will work as follows. I pick a number between 1 and 0, 1 and n. You guess a number. If you guess the right number, you win the game. If you guess the wrong number, then I will tell you whether the number I picked is higher or lower, and you will continue guessing. Every time you guess a wrong number, you will pay X dollars. If you run out of money, you lose the game. Given a particular n, return the minimum amount of money you need to guarantee a win, regardless of what number I pick. That is interesting. N is 10, right? And if I got wrong, I have to pay X. So guess a wrong number and then pay X. Okay. The range, guess 7. If this is my answer, your total is 0, otherwise you pay $7. If my number is higher, your range is 8 to 10. Guess 9. If this is my number, your total is 7, otherwise you pay 9. If my number is higher, it must be 10. Guess 10. If the number is lower, it must be 8. Guess 8. If my number is lower, the range is 1 to 6. Guess 3. Because my number is 7, otherwise, if it's higher, the range is 4 to 6, which you need to pay one more time, right? You need to pay one more time. It's $10. Well, this one is $10, so I have to pay one more time, so it's 15. And on the other side is just 4. 3 plus 1, 11. One possible number, so you can guess. If it's 2 values, right? Let's see if we can understand this. If 2 values, if I guess 1, I'll always guess the lower one. I guess 1, I either win or I lose. Then I need to pay 1. Yeah. So, what value should I guess? From 1 to n, right? Now, the best strategy is to guess the middle, right? Because you guess the middle, you split it in half. Well, let's go 1 to 5 again. So if I do 1 and 5, so I guess 5. If it's wrong, next one, I have 6 to 10. Then I'll guess 8. Wrong again. So the next range, yeah, we don't need to go to the higher range. The lower range, we don't need to go. And then that's, if 8, I guess 8, right? Because it's 6 to 10, 8, and then I have on one side is 6, 7, the other is 9 and 10. Oh, 9 and 10, that's it. So 5 plus 8, it's 13. Oh, but that's the worst case scenario. You want the worst case scenario. To guarantee a win, regardless of what number I pick. So that is, so it needs to be slightly biased. I mean, of course, the slightly biased. The smallest situation that guarantee whatever, which means if I start at any other position, it will all be lower than this. If I start at 10 and I say guess wrong, and I go 9, I guess wrong. How's that work? The minimum amount to guarantee a win, regardless of what number I pick. Okay, this doesn't make any sense. What do you mean the minimum number, regardless of what number I pick? Well, what if I pick 10 and it's wrong? And then I pick 9 because you say it's smaller, so I pick 9. And it's wrong, then I'm already out $19. What is this question looking for? The worst case is not you pay $1. The worst case is you pay $2. Why do I guess 1? I can guess 2. I guess 2 and I pay $2. Hold on. I don't understand. What is the rule? What is the rule? I pick a number between 1 and 10. Okay. And you guess a number. If you guess the right number, you win. If you guess the wrong number, then I'll tell you whether the number I picked is higher or lower. And you will continue guessing. And every time you guess the wrong number, so I think the thing is, the minimum amount of money you need to guarantee a win. Oh, regardless of what number I pick. But hold on. Given n is 10, regardless of what number I pick, I can start guessing at 5. I always start guessing at 5. If I guess at 5, then I only need 13. Whichever number you pick, I only need $13. I guess 5, and then you say it's too small. Okay, I pay 5, and then I guess 8, right? And you say it's too, right? Because it's balanced. The tree is balanced. Wait, is the tree balanced? Hold on, I'm still in a confused stage. If I get 5, right, and then on the right side, I have 6, 7, 8, 9, 10, right? On the right side, I guess 8. Oh, if I guess 8, it doesn't split. If I guess 8, and you say it's too big, and then I have 9 and 10, and then it's 9 and 10. Ah, I see. Now it makes sense. Now it makes sense. So this is bad. This is bad. Ah, okay. It makes sense now. So in this case, what we want is to have as balanced a tree as possible. And after we can balance the tree, we want the right branch to be shorter, because the cost is going to accumulate on the right side. And how do we do that? Like we want to have this scenario, right? After we do it, and I would go, I would guess again, right? And then we guess again, it shall split, right? It shall split. And after split, the remaining shall also split, which means each value I guess, I shall have the larger to be, like, I should pick a value such that the value larger than me should have 3, right? And the value smaller than me, ideally, will be 1, 2, 3, 4, 5, 6, 7. So shall be 2 to the n minus 1. That would be the ideal. But if I cannot get it, it's fine. On the left side, we can do this. Okay. So this strategy is always going to get the largest value on this side. Well, that's debatable, right? That's debatable. And it depends on how large the number is. So what I think is we want a balance, right? We want a perfect balance. And on the right side, I want one level lower than the left side, right? So given a value, I think what we want to have is to have on one side is 2, let's say if on the right side, say 2 to the h minus 1. On the left side, we want 2 to the h plus 1 minus 1. Or 2 to the h plus 1 minus 2. Doesn't matter, one of these. And then, so that's what I want. All right, that's what I want. So either, oh, they also can have the same. They also can have the same length. All right, so given each value, I aspire, right, to split into, so that's a 10, right? So I guess 1, so I have 9 values left. Ideally, if they are equal, right, that would be ideal. If equal, it's actually not ideal. If they're equal, and they can be, if they're equal, they both have to be 2 to the h minus 1, right? So we can do this times 2 equals this, which is 2 to the h plus 1 minus 2 equals whatever value. So we can check to see if it makes sense. And if it is, right, which means, let's say, 7, we have 7, right? If we have 7 values, 1, 2, 3, 4, 5, 6, 7, so we can do 4, 2, 1, 3, 6, 5, 7. So the answer shall be 10. That's my understanding. Let's see. Can you prove it? I cannot prove it. I mean, what I can prove is the deeper you go, the more expensive it gets, right? That's for sure. The deeper you go, the more expensive it gets. So we try to make it as not deep as possible, okay? Which means we want to make it balanced. So we try to make a balanced tree, right? So I actually try, say, turn 0. Yeah, but the proof side is not that strong. The game is not strong. We can try, I think it's 7 that I'm trying. 7. I think 7 is going to equal to 10. $10. Yes, $10. So that's one we can split, right? Okay, so if at the root, I already know that we can split evenly. I add it, and I go to the left and right, and at each root, I try to see if I can split it evenly. Well, what if I cannot split evenly? So we have 2 options, right? So the options are one side is 2 to the h minus 1, the other side is 2 to the h plus 1 minus 1. So that's one situation. Another situation is 2 to the h minus 1, and the other side, I mean, what if I can remove this? Like evenly distributed is good, right? If we cannot evenly distribute it, then we want this one to have one more branch, right? Which means we're going to do one more wrong guess here. Okay. So all I need to know is to get this side, right? Okay. How do I get this side? So I remove 1, I have 1 value. Now I have the remaining value. Now all I want to do is to check, right? So I check if it can be evenly distributed. So I say we do 2 to the h minus 1 times 2 equals whatever this value is. So this can give me an estimated height if we want to do the same. And if it fits, perfect. If it doesn't fit, what would it mean by it doesn't fit? Well, it doesn't fit just means, like, if it's too much, then it will be like a decimal point, right? So whenever I have a decimal point, I will reduce it. I will take the floor. Okay? I'll take the floor. Let's try it. So I have 9. Right, so 9 divided by 2 plus 1. And we call log this divided by log 2. So it's 2. So I say I'll take h equals 2 on the right side. So when h equals 2 on the right side, what we got on the right is a 2 to the 2 minus 1 is 3, right? So we need to have 3 values on the right with this, right? And then if it's 3 values on the right, so we can deduce 10 minus 3 is 7, so the top must be 7, right? And then we can go to the right, and we know because it's 3. So 3, so we know that's 8, 9, 10, right? So we pick the middle, right? We pick the middle. Yeah, I think the idea is always to make the right side a perfect binary tree. So on the right side, we pick the middle, and then we get to 9, and we're going to record 9, and then we have remaining, right? And the remaining, they have their range. So we will always get their range, a lower, higher bound, and get their range, get the middle, and 1, so I get the middle, and then we go down, and if it's by itself, then that's it, right? And now on the left side, because it's 3, so 9 minus 3 is 6. So on the left side, we have 6. Okay, so if 6, then that means 1 to 6, right? 1 to 6. So 1 to 6, I have 6. So 6 minus 1 equals 5. So we're going to split 5. So again, it's the same thing. 5 divided by 2 plus 1. And I log this divided by log 2. That gives 1.8. So we take 1. So the right side, I want 1. Which is now 1. The right side is actually 2. This level 1 is just going to be 1. This is going to be 6. It's going to be 5. This method doesn't work. It doesn't work in this situation. Now we have 5. And then that's almost 2, right? Almost 2. Almost 2. And I'm on the left side. I would try to balance them, right? We want to balance. I mean, it could be like, we can put like, say, 4, 2, 1, and 4. Two and 3, right? And then 5, and then 6. That is also balanced. And this one is going to be 4 plus 5 is 9. 9 plus 7. But in this idea, I'm going to have 5 and 6. Right? So I want to take 1. On the left side, we have 4. Yeah, 1 to 4. 1 to 4. If I take, I have 3 left. Right. 3 left. 3 divided by 2. Plus 1. Log this one up 2. Plus 1. So I will have 1. So it's 1 to 4. I have 1 So that's going to be 3, 4, right? And then 1 and 2 on this side, 1 and 2. Well, if it's 1 and 2, I'll just take 1 and 2, like this. If this, it can be 4 plus 5 plus 3 plus 1. So now 4 plus 1 is 7. It's also 16. Are you telling me this one's right? That doesn't seem right to me. There's so many ways I can make it better. Now the idea is I want to balance, right? I want to balance the left and right tree. If they have the same height, it'll be good. But I cannot have them have the same height. Hold on, I'm going to try it again. So I have 9 nodes, right? So it's a 2 to the 2 minus 1 is 3. That's within. 2 to the 4 minus 3 minus 1. 7. That blow up. So I want 3 and 3. So on the right side is 3, the left side can be 6. Right? So on the right side we have 3, left side we have 6. So now the question becomes, given 6, right, what is the smallest? We're given 6. Well, the smallest 1 to 6, and then minus 1 would be 5, right? 5 we can do 3 plus 3. That's too much, but that's within a reasonable bound. Right? So if we don't do that, right, we don't do that, so we have 1, and now we have 5 left. With 5 left, we can do like 3 on one side and 2 on the other side. So we can 3 on this side and 2 on this side. Because the choices is always, it's 1, 3, 7, right? So if we do 1, then we have 1 and 4. In 3, we have 3 and 2. How do we reason? How do we reason this? We want the difference to be smaller. Okay, so we're given 9. So what we can have is 1, 8, right, 3, 6, 7, 2. That's the option. And among these options, apparently 3 and 6 give us the smallest difference between the two. So that's why I picked 3 on one side, 6 on the other side. Now I have 5. 5 I can have 1 and 4, and we always want, it doesn't really matter, big or small. So I have 1 and 4, 3, and 2. We want the full on the right side. Okay, 3 and 2. And that's it. So 3 and 2 is better, so we'll pick 3. Right, and then after I pick 3, then we start with 3. Now we have 5 here. So now we have 3 values. If we have 3, then it's just set in stone. Right, just set in stone. So we have 3, we just return this, and that's it. On the left side we have 2, right? And then we have 2, then it's also set in stone. There's 1, 2, we always take 1 and then leave 2. I want to do a a bigger value. Let's say, how about 20? Okay. So 137. What's the next one? 15. 31. Right. So let's say I have 20. So I have 19 to split. Right. 19 to split. Now I want to make it as even as possible. So we do 19 divided by 2. Let's give us 9 point something. So we're looking for 9 point something. We're going to get 7 or 15, right? So let's say we do 7. That's going to be 7 and then 12. Then we do 15. That's going to be 15 and 4. So 7 and 12 result in difference of 5. 4 and 15 results in difference 11. Okay, so we prefer 7 and 12. Okay, so now on one side is 7, so the root is going to be 7. And now on the right side is going to be 8 to no, it's not 7, it's 20, it's 13. The root is going to be 13, on the right side is 14 towards 20. Right? Now because it's 7, right? So we just need to pick the middle part. Yeah, so 7, so we just need to pick the middle part, which give us 17. So 17. And then to the left is going to be 14 to 16. Pick the middle part, is going to be 15. On the right side is 18 to 20. Pick the middle part is 19. So these are the values we need. 13, 17, 15, 19. On the left side I have 12. Okay, so it's 1 to 12. So we have 1 to 12. Then what? We have 11 values. We're going to pick. 11 values divided by 2 equals 5. So the result is between 3 and 7. So we have 3 and 8, or 7 and 4. So 3, 8, difference is 5. 7 and 4, difference is 3. So we pick 7 and 4. So again, we have a 7, right? So this is 1 to 12. And 7, so we're going to be 5. So 6 to 12 on one side. 6 to 12, because it's 7, we're going to divide it. So that's 18, so we're going to get 9. So it's 6 to 8, 10 to 12, and 9, 7, 10 to 12, and be 11. All right, 10 to 12, that's going to be 11. And 5 as well. So on the left side is a 1 to 4. So 1 to 4. 1 to 4, if we take 1 out, we'll have 3 left. Divided by 2 is going to be 1. So it's going to be 2, 1, or 0, 3. Of course, we pick 2, 1. So on the left side is 1. That's a 1 to 4. So we're going to get 3, right? And the 4 doesn't really need, because it's only by itself, so that's fine. Left side is going to be 1 and 2. So 1 and 2, we always go 1 first, right? 1 and 2. So basically, we say that 2, right? 2 minus 1 is 1, divided by 2 is 0. So it's only be 1, right? So it's going to be 0, 1. So we're going to go on the right side is 1, it's going to be 2. So it's going to have 1, 3, 5. Okay, we need to calculate the maximum sum. So maximum sum on the right side is going to be 13 plus 17, we're all going to keep always going to the right, right? And plus 19. 49, right? That's 49 cost if we go on the right side. Now go on the left side, right? On the left side, we're going to accumulate the highest cost, the highest cost. So we have 5, I don't know. So this one 9, so 9 plus 11 is 20. There's 20 on this side. And this side is going to be 3. Only 4, so it'll be 20. So plus 5 is 25. Right? So that's 25. 25 plus 13. 38, so it'll be 49. Not sure. 20. If it's not 40, it's not now 49. We're just gonna give up today. Try to think about it tomorrow. Is that 49? It is 49. It is. So I think this idea might be right. So the basic idea is we want to make both trees as balanced as possible. So they need to have similar numbers. And then I want the right tree to be completely balanced. Right? If the right tree is complete, because the complete balance means you need to go the minimum number of depths on the large side. Right? Okay, see if we can code it up. If we passed all these, so give me some hope that this might work. All right, so the next goal is to see if it works. It's already late, so how many times I say this? So we're gonna just try maybe just this method. All right, if this method works, hallelujah. If it doesn't work, I'm not gonna stress about it. I'm gonna try it again tomorrow. It's fine. Chill. All right, chill. Okay. So what do we got? Get money, right? Get money. I need to rewrite this function. Def helper. I'm gonna have a low and a high. Right? And this one will return integer. So we have a low and a high. Now what we're gonna do is because the total number is 200, right? So we're gonna have a list of sizes. We have 1, 3, 7, 15, 31. What's the next? The next is 64, so 63. What's the next? 128, 127, 250. I'll blow it up because we have at most 200. So that's it. That's all the sizes, right? So once we get it, we need to say half will be equal to half the size will be high minus low plus 1 divided by 2. Right? So that's half the size. So now we're going to just look into the side to see the most appropriate. Right? The most appropriate. And we can just say, I don't know, so for I in range len sizes, no. For is in enumerate sizes, we'll find the first one that's bigger. So if s is bigger, right? If s is larger or equal to, half, then we're going to break. Okay, now we have I. So we're going to point at something larger or equal to, right? Then the first thing that's larger than equal to this. So it's I and I minus 1, right? Two options. So what do we do? So we're going to pick an option. So option 1 is going to be option 1 is going to be, so left 1, left 2, left 1, right 1 shall equal to a sizes, right? Okay, hold on. So we break out. Now we say if s is equal to half, right? If s is equal to half, then that means we can split into half. So that's perfect, right? That's perfect. Yeah, if it's equal to half, then we can split into the half, and then we just need to call, if s equals equal to half, we're going to call helper, right, on the right side. So on the right side is going to be the high by minus s plus 1, and the high, that's on the right side. And then on the left side, right, on the left side is also helper. It's going to be low, all right, s low plus s. So if low is 1, and I say s is 3, so 1 plus 3 is 4. So 1 to 4 has 4 values. I might only need 3 values. All right, I only need 3 values. So it's minus 1. Okay. So if we're going to return high minus s, that's the current one, right? That's the current one. Then plus the maximum of this. And why don't we just cache it, just in case? Now you cache, and we just cache it. Okay, so if s is equal to half, then I have a bunch of this. Now if s is not equal to half, is larger than half, we say if I is equal to 0, right? So that is the case where I is 0. So this one is larger than, which means this one equal to 0. So I is 0. So in that case, I will only have, actually no, let's just say if I is larger than 0, right? If I is larger than 0, so I have two choices, either I or I minus 1, right? And then we say, I basically want to compare the absolute difference between the two. We say if yes, this is larger than or larger or equal to. Remember, we want ABS the other side. So what is this side? This side is going to be sizes I, right? Sizes I, and then minus hold on. It is because high minus low is a total number, but we need to take one out. So the remaining is this. So that's going to be minus high minus low, right? Minus, so remain equals high minus low, right? Then half equals remain divided by 2. And this is going to remain minus sizes I. Right? And then we're going to do the exact same thing. But this time is I minus 1. Minus 1. Alright? Alright, what we're saying is size is a worse choice compared to I minus 1. Therefore, I equals I minus 1. That's it. So if this, right, and this I equals I minus 1, I pick I minus 1. Otherwise, I'll remain as I. Okay? Now, the right half is going to be I, and the left half is going to be whatever. Right? So, in this case, I'm going to return high minus S, no. The right side is sizes, I plus max helper, this, helper, this. Okay, so let's go handle the right side first. Right side can be high minus sizes I plus 1 high, right? And then there's going to be low, low, so high minus sizes, right? So shouldn't that just be high minus sizes I, that's in the middle, minus 1, which means this is just going to be high minus S minus 1. Yeah, that's true. Okay, so that's that. Return this plus the maximum of this. Now, here's the thing. If I come to a certain point, right, for low and a high minus this, if it's equal, right? If low and a high becomes equal, actually they will not become equal. If remain is 1, which means half is 0. If half is 0, which means low and high are adjacent. I mean, if low is, if a value is by itself, it shouldn't happen. Because I try to balance the two, right? I try to balance the two. So if I try to balance the two to make them as close together as possible, then if it's 1 and the other side is 3, right, that's going to be 4. But in that case, it's not going to be this, because 1 plus 3 yeah, that is going to happen. Okay, so we're going to say if low is equal to high, return 0, because this one we don't have to call. Because that's just sticking out, right? We don't have to call. If high minus low is equal to 1, then we return if high minus low is equal to 1, right? Then we return low. Otherwise, we do all this. I mean, even if s is equal to half, it doesn't matter. If x is equal to half, then these two are the same, right? So I don't have to, this is not a special case. And we simply just do this, and then we return. Okay. Now, what do? We're going to return helper. Low is 1, high is n. Okay, so we have lots of test cases. We have 1, which shall return 0, 2, which shall return 1, 3, we don't have 3, but we have 10. 10 shall return 16. 7, I have 7, shall return 10. 20 shall return 49. So these pass. Okay. We can test every single one of them. I just realized that. I mean, if you think about it, all we need to do is just print from 1 to 200, right? I can just do this for I in range 201, 1 to 201, print I. We can trick that's it. That's it. 200 is not that big. We can abuse it. And okay, I ask it to test every single value. And if anything is wrong, then we know and try to fix. Oh, something is wrong. Yep. First thing wrong is 1, 2. Wow, that's pretty bad. I think the first thing wrong is 22. 11. 11. That's the correct answer. Yeah, it should be 18. I got 22, so that's not right. 11. Okay, let's see what happened with 11. What is a good strategy for 11? 11, 11, 11. I think I'm gonna use my thing. I'm gonna go 3, 8, 7, 4. So in my mind, I'm gonna go 7, 4. So I have 7, right? And that's 8 to 11. 8 to 11, 9, 10. No, that's 4. No, wait, hold on. 11 is 10. Oh, 3, 7 or 7, 3. Hey. 3, 7 or 7, 3. Okay, let's say 3. Okay, if it's 3, that's going to be 7. So it's 8, 9, 10 values, right? So we have 11, and 3 is actually 8. So 9, 10. Okay, on the left side, I have 7. So it's 1 to 7. So 1 to 7 is 4 in the middle. And then there's going to be 5 to the 7, 6 here, 1, 1, 3, 2 here. So we're going to add 18 on this side, 18 on this side, 14 on this, so it's going to be 18. But I got 22. I think I got 7 and 3. Okay, so I got 7 and a 3. That's what I guess. So if it's 7 and 3, so the right side is 7, and so I got 4, right? And then 7, that'll be 5 to 11, that'll be 8, 5 to 7, that's going to be 6, 9 to 11, 10, 22. Yeah, that's the problem. So basically this is just means, I mean, we can actually copy and paste this whole thing. This is this official solution, right? So what we're gonna do. This is the start. No. No. Okay. So we're gonna this. So we're gonna replace with a what? This. Ew. It's hard to do. Yeah, this is hard to do, man. We need a. All right, let's just get the wrong. So 11, right? 11 should be 18. Oh, take a few, right? 11 is 18. 12, 13, 14, 15, 16, 17. Okay, we just go to 17. Okay, 12, 13, 14, 15, 16, 17, okay? So what's 12? 12 to 21. 13, 24, 14, 7, 15, 30, 16, 34, 17, 38. Okay, a lot of test cases. All right, so what is this? So this is fine. Now we find this. The first one is larger. Then we always find the between 3 and 7. So if it's larger, then we do this. If it's equal, larger equal, if it's equal, because I is the bigger one, right? So if it's equal, also I to get a smaller one. Okay, run this. Yeah, I don't need to print this, come on. This is just stupid. No. So we passed this, but we fail. Wait, which one we fail? 21. So 21, I got 25, that's a 24. So 12. What the heck? What is 12? So 12, which means I need to find 11 values to split. So 11 values divided by 2 is going to be 5. So it's still 3 and 7, right? So we got 3, 8, or 7, and 4. Apparently 7 and 4 is better than 3 and 8 because it's more balanced. But it also means 4 and 7 is more on the 7 side. Right, so if that's the case, then 12 minus 7 is going to be 5. On the right side is going to be 6 to 12. That's going to be 9. And that's 7, 11, 25. Okay, what if it's 3? If it's 3, then what we have is 4 minus 3 is 9. So 10, 11, 12. And then on the left side is going to be 1 to 8. Right? Now 1 to 8, we'll do it again. 1 to 8 is 1 to 8 is 8 values, so 7. That way 2 is going to be 2, so we are between 1 and 3. So it's either going to be 5, 3 or 7, 1. Alright? 5, 3 or 7 and 1. So apparently pick 5 and 3. So 5 and 3, 8 minus 3 is 5, right? And then we're going to have 6, 7, 8. On the left side we have 5 values, which is 1 to 4. Oh no, that's 7. Yeah. 7, 1 to 4. Okay. So 1 to 4. 1 to 4. So 1 to 4 is going to be 3. So that's going to be 1. So right side will be 1. 1 to 3. So that's 4. But then count in a 1 and 2. So this one will give us 20 on this side. And this side will be 21. Or here 17 to 21. Okay, so the rule is still wrong. It's only come out, right? We need a smaller one on the right side. So what do we do? So we have sizes I, right? And then we have remain minus sizes I. So we need to decide which one is bigger, right? So, so if one option, yeah, so I have two options. If one option is bigger than the other, okay? All right, so I have a few ones. So we say if I is larger than 0. And then we say if remain minus sizes I is remain minus size I is larger or equal to sizes I. Okay, so if the remain minus size is the left side is larger or equal to the right side. It should be like this. If this is smaller, if remain minus sizes, the left side is smaller than the right side, then oh, hold on. No, 7 minus 2 is 3. So we get 3. And then we get 1. Yeah, this type of thing happens. This type of things happens. Okay, so what's the rule? So if both fit, then we pick the one with the smallest difference. If both don't fit, then we should pick the one with the smaller on the right side. If one fit and the other one don't fit, we pick the one that fits, right? So we always pick the one that fits if the other one does not fit, which means if any one side then it got to be with a smaller one, right? Because it's always the bigger one, right? The size I is the bigger one. So if the bigger one flipped, right? So if remain minus the bigger one is smaller than this, then I equals I minus 1. Okay? Else, so the big one does not flip, and the small one will not flip as well. So if now we need to try to see, so neither flip. So when neither flip, which one will be the better solution? Do we want to get them more equal, or do we want to, well, if neither of them flip, then neither of them are big, right? So then we just try to balance them out. So now we're going to use this. So if this one is larger or equal to, well, I mean, you know, sizes I is always larger than sizes I minus 1, right? So in that case, if the larger size doesn't flip, then we should always pick the larger one. Which means I think that shall be the only one. If this and because it will never flip, we just say the larger one flipped, right? The larger one, because we'll get the remain minus the larger one, will be smaller. So this one flipped, so we pick the small one. Otherwise, if this one doesn't flip, we always pick the larger one. Try now. All right, we've passed more, but we still fail. What do we fail at? 15. 15. Okay, 15, so we have 14, we have 7 and 7. Okay, so there's 8, right? 8 in the center, and then we have 9 to 15, and a 1 to 7. Okay, 9 to 15 is 7, and then 7 we can split. 7, that's 6, that will be 3 and 3, right? 3 and 3. So 3 and 3. So 15 minus 3 is 12, so we have 12. And then 13, 14. And then here is going to be 9, 10, so 10. So that's 34. That's 34 for you. So this logic doesn't work. Now how do we do 15? I think maybe the idea should be one side needs to be smaller than the other side. So in 15, I have 7, 7, or 12 plus 3. I think the idea is we're going to get 3. So basically, if there's 3, that's 14, 14, 14, so it's 11. And it's 7 and 7, right? So it's 15 minus 3 is 12, right? 13, 14. So 12, 14 on one side. And on the other side, we have 11 values. So 1 to 11. 1 to 11, basically when you're trying to find 11, what's 11? 11 is 18. The max is 18. So that one gives us 30. Shoot. Huh? Shoot. Okay. So what do we say? We always want on the right, so if the two can balance, so we always want the right subtree to be lower than the left subtree, which is understandable, right? It's understandable. We want the right subtree to be smaller than the left subtree. So when we get out, if flipped, then definitely. If it does not flip, right? If it does not flip, then I say, so basically I do this. If it's equal, then I don't like it, right? I don't like it. I will go for the smaller one. If it's too big, then I'll go smaller, smaller. Now I'll stay with I. If remain minus this is larger than. Let's see if this one. How is it still not right? Maybe a 32. I don't know. I minus 1, shouldn't it be 3? Okay, on the left side is 11, and 11 passes, right? 11 passes, but this one does not pass. Wow. All right, isolate. Isolate 15. Okay, I'm gonna do some debugging. Blah blah blah. I'm gonna say if I like 0 and the remain minus this is smaller equal to, right? Then I is gonna be this. So let's just print sizes I. Okay. So sizes I is 3, which is understandable. Sizes I is 3. If sizes I is 3, then it's going to be high is 15 minus 15 minus 3 is 12 plus 1, 13. So 13 to 15, right? So we come in 13 to 15. 13 to 15, 13 to 15, and then this one, 13 to 15. All right, let's set up a rule on this. I think it's because it's 13 to 15, and then this one will get half a 1, right? Now we have 1, I is 1, and then remain is 2, right? So 2 minus 1 equals 1, then I pick a 0. No, I did not pick 0. I is larger than I is equal to 0. I is equal to 0. Yeah, there's the first one. I is equal to 0. So if I is equal to 0, and don't do this, then what is I? I don't even have I. Well, I is 0. So size of 0 is 1. Isn't that correct? Size is 1. So I do low, high is 15, minus 1 is 13. So that's going to give me 0, and then this is high is 15, minus 1 is 14. Yeah, it is 14. Minus 1 is 14, plus 1 is 15. So these two shall give me, so I cannot, I need to print low and high. So 115 and 111. 111. That is true. 111. 111. So I have 12 on here, so this is going to be 111. And then we do 17, which means it's 8. Yeah, so 111 is 17. And then we're going to go 15. That is trouble. 17. 1, 2, 7. 1, 2, 7. 7 values. 6. 1, 2 is 3. So come out as 3. 3 and 3. Right? So 3 and 3 is no good. So I go 1 and 3. 1 and 5. So what's the rule? Like if the tree is big, then it is equal, because this is on the left side, right? So on the left side, they're all small, so we shall, how do you even, okay, so if it's on the right branch, then we want to eliminate. If it's on the left branch, okay, so we add another one, left or right, right? So it's left or right. If it's equal, and on the left branch, then we want all equal, right? And if it's on the right branch, we have the situation, then we don't want to be equal. God, that is just not making any sense. It doesn't make any sense. Why? Why on the left side and on the right side? Like, where on the right side? Now I understand. Like, this is just you see, we have 3, 3, 5, 5, 7, 7. Everything is just by itself. That's why it accumulates too much. Maybe this is not the right way to think about this problem. Maybe we should just traverse. I mean, we don't have 200 nodes. Right? We don't have 200 nodes. Even if O squared, and then we can cache along the way. Okay, so we start from the center. No, we start from the front. Right? We start from the front, and we have a left and right, and then we can always record the value. So the next time I do it, I don't have to go, okay, let's ditch this. We don't need this. Right? Helper is going to be this. What I want to do is I want